Yes, that's really the inspiration for this video. The question is, are circular sectors best packed in circles? Or is there another method that can do better? For the math-inclined viewers, I'll flash up some technical details right about now. One note before we get too far into the weeds: if I ask a question that piques your interest, or you think you know where the explanation is going, I'd recommend pausing and trying to work it out for yourself. Or just keep watching, and I'll tell you how it works. I'm not your boss. One shape you've certainly seen packed before is the square. Squares play nice. They let us pack them into neat rows, with their straight edges all perfectly aligned. There isn't just one way to arrange squares, though. You can slide their rows and columns around to produce a lot of different patterns. Unsurprisingly, rectangles can replicate this behavior. With them, though, we can even go beyond the simple lattice structure with rotations, which open up a whole new set of packing configurations. Triangles are up next. We can't just line them up like squares and call it a day. That would leave a lot of empty space behind. But with a little bit of rotation, we can slot more triangles into those gaps, forming interlocking strips which cover the plane nicely. Finally, we have hexagons, which are quite particular. There's literally only one configuration that lets them cover the plane. Not the most interesting result, since we can't tweak anything about it, but I guess perfection isn't always flexible. All of these packing structures have two things in common: straight touching edges and a degree of symmetry that makes the structure repeatable. We'll want to keep all of that in mind for our own packing needs. Now, let's take a step up in complexity and look at circles. The nice straight edges that made our previous packing problems perfect have been replaced with frustratingly inefficient curves. We're guaranteed to have some gaps between our circles, but how can we minimize those gaps? We could try, for example, to lay out the circles in a square lattice, or maybe slotting them into a hexagon lattice would be better? Okay, we're quickly running into an issue of rigor here. You'd probably agree that the hexagon lattice looks more efficient than the square lattice, but we want to prove that one is better than the other definitively. How can we put a number to this idea of good versus bad packing? Packing mathematics gives us a simple answer: density. For any given packing arrangement, we really want to compare the space inside the packing to the total space surrounding it. If we divide the inside area by the total area of the arrangement, we get a single number that quantifies how full our packing is. Increasing the amount of filled space in our packing increases the density proportionally. Now, for a finite structure, that would be enough, but unfortunately our packing structures are infinite, so we can't just measure their area directly. Instead, we can use another trick from packing mathematics: the tile. The idea here is to pick on a small, finite section of the packing that can recreate the packing using copies of itself. We can measure the tile's density directly because its filled and total areas are finite. By definition, the packing can be made using just this tile, so the packing must have the same density. On this tile, for example, we can define a radius r for the circle to find its internal area is pi r squared. The square will have a side length of 2r and a corresponding area of 4 pi r squared. Dividing these two areas gives the tile a packing density of pi over 4, or around 78%. Since the square lattice packing can be made using this tile, that gives us the density of the packing as well. The hexagon lattice follows a pretty similar logic, just using a hexagonal tile instead. We can find the hexagon side length by forming a 30, 60, 90 triangle from the radius in the hexagon side. The short leg of this triangle is a factor of root 3 smaller than its long leg, and the hexagon side length is twice that. Then we simply plug that side length into the regular hexagon area formula. Dividing pi r squared by this area gives us a density of around 90.6%, which is much better than the square method. And this, as it turns out, is the most optimal packing configuration for circles. It's worth noting at this point that a packing structure can have many different tile shapes. Deciding between them is mostly a question of convenience. As long as it can be used to construct the packing, it can be used to calculate packing density. At this point, we've laid enough groundwork to get to the question at hand: how can we best pack circle sectors? Well, let's start with the obvious answer: making them back into circles. From there, we can pack the circles into the optimized hexagon lattice we just analyzed. For some sector shapes, like semicircles and quarter circles, this seems to work out pretty well. But for sectors that can't fill a circle cleanly, we're stuck with this Pac-Man structure that wastes a lot of internal space. If we tile the plane with these Pac-Men, what's their density? Each circle has an internal angle of 2 pi radians. If we assign an angle theta to each sector, we can fit a total of 2 pi over theta sectors inside the circle, rounded down. Each of those sectors accounts for theta over 2 pi worth of space inside the circle. Multiplying these values gives us the proportion of each circle that's actually full. We just found the density of filled circles in this structure, so we can multiply by our new proportion to find our Pac-Man packing density. For a little perspective, we can plot our density for every sector angle, shown here in blue. It's pretty clear that this density is capped at some value, which turns out to be the 90.6% density of the standard circle packing, drawn in orange. Now, we could keep iterating on this method. We could slot the Pac-Men into nested lines, or try to start rearranging them into more efficient groups. But to me, this whole method feels a little uninspired. Sectors are interesting entirely because they aren't full circles, and this method forces them back into that pre-existing mold. Okay, from here, I'd really encourage you to pause for a moment and try to consider how else we could arrange circular sectors. This realization is what tied the whole project together for me, so it'd be a shame if you can't enjoy the same moment for yourself. When you're ready, come back and I'll talk you through my solution. Alright, here's my pitch. Let's keep the straight lines of each sector touching, but flip the orientation of every other sector, and then continue that pattern along the plane to form these sector strips. They're kind of similar to the triangular strips that we looked at earlier. We can then slot these strips on top of one another so that their curved edges are tangent. I haven't seen this method discussed anywhere yet, so I'm going to informally coin it the sector connector. So, we have a proposed solution. We're back to the same question, though. The method looks quite dense, but is it mathematically more dense than the Pac-Man method? First, we need a tile. Unlike our previous shapes, we can't just put the sector in a box. Doing so cuts out the gaps between our blue sectors, which means that this tile won't actually replicate the packing. We're close, though. If we bring the ceiling of this tile up to touch the bottom of the next sector, it's able to replicate the packing properly. Now we need the density of our tile, which means we need its filled and total area. Conveniently, this tile contains exactly 2 sectors worth of filled space. We can demonstrate this by a quick rearrangement of its pieces. A single sector has an area of r squared theta over 2, so 2 sectors will have an area of r squared theta. Calculating the total area of this tile is a little more delicate. The width of this tile is the same as the width of the sector. This length forms a chord with the external points of the sector's arc, so we can find it using a formula for chord length. To find the height, we'll need to look at the broader tiling structure. Starting from our defined radius and angle, we can construct a series of triangles across the sectors to work towards finding the tile's height. This process might look complicated, but the formulas used are simple. We can make our way to the tile's height using nothing but right triangle trigonometry, the law of sines and cosines, and the fact that the angles of any triangle sum to pi radians.
All that being said, this process does take a while to mathematically work through, so sit back and relax for a moment as we work towards the height.
The tile's total area is just a product of its width and height. And finally, the tile's density is found by dividing this total area by its filled area, r squared theta. As with before, we can plot our solution against sector angle to see how it performs. Here the Pac-Man method is shown in blue, and the circle density is shown in orange. Plotting the sector connector, shown in green, reveals that it outperforms the Pac-Man method across all sector angles. Notably, though, even the sector connector dips below the circle packing metric for certain very large sectors. So, we have a solution. Is it airtight? No, of course not. It's possible that improvements to the Pac-Man method could put it above the sector connector. Or maybe another method exists that blows both of these arrangements out of the water. But I think the sector connector is beautiful, and it highlights the unique nature of circular sectors, so I'm happy with it.
Hey, thanks for watching, and especially for sticking around to the end. Normally this is where people would promote something, but honestly I haven't done anything like this before, so I don't have much to promote. Maybe go eat a waffle? I heard those are pretty good. Okay, but genuinely, a few quick thanks are in order before I sign off. I want to thank TD for sending the actual waffle text that inspired this project and for supporting all of my crazy ideas. Thanks to Aiden for swapping stories about our different projects and for always asking how my animations were coming. Thanks to Lauren for the artistic design work and for showing an interest in even the most mundane parts of my math and programming. Thanks to Ali, Junyoung, and Isaiah for sitting through my insane rambling beta version of this video, which was in PowerPoint form. Thanks to Napaka for encouraging me to actually make this, and for keeping me on the hook to finish it. And again, thanks to you for watching this.